So 3.2. I think it's logarithmic functions, or inverse functions and logarithms. So that's the calculus one. So let's take a table and let's do this. Let's take a table one and we'll label it a function of n, or of t, I mean. And we'll do so such that t is going to be 0, 1, 2. We'll just do 3 because I don't want to write everything out. Pretty lazy. So we'll do 100, 163, 259, and 358. Which is, I believe, the table they use in the book. And then we'll do the same thing here, which is going to be a second table. And this time it's going to be table 2, and it's going to be n, or t of n. In other words, we're taking the output of this function. I guess the more correct notation would be t of n of t. So it would be t of n of t. But I was, or the book says t of n, which all that means is you take the input now, and guess what happens here? We'll say n is the input, we'll say t is the output. It'll take the output of the original function and transform it back into the input of the original function. And this is what an inverse function essentially is, being able to restore the input of a function by applying a reverse transformation. That sounds a little bit complicated, but we'll get into that a little bit more. Before we start, we have to note that the notation for an inverse function is f prime of 1, or not f prime of 1, f to the power of -1. Well, it's not actually the power of -1, because if it was, it'd be a reciprocal. But people assume that this is 1 over f. But in reality, it's just going to be the inverse function, such that f of -1 of f of x is going to equal the original output. And I believe the product of the two becomes 1. But we'll get into that later. So not all functions have inverses, and we'll get into that right here. F of x equals x squared. So let's take, a lot of people think that the inverse function of this is going to be square root x, such that if you do square root of x, or f negative 1, or sorry, yeah, the inverse of f of x, you get x squared, which equals x. Now, here's the fatal flaw. Squares removes negatives, and square root doesn't know that. In other words, let's say that we say f negative 1 of f of negative 2. So that means we first do f negative 1 and we value the inner function, which is going to be negative 2 squared, which is just 4. And the f negative 1 of 4 is just going to be square root 4, which is equal to 2. We don't get the original point back, instead we get the negative function. In the same way, square root x is not really the inverse of x squared, though many teachers make you believe so in the early algebra and pre-calc, because we don't get too advanced into functions yet. But that's the logic behind it. This function is only defined for positive positive outputs, and that's just the way it was defined. You could theoretically do negative outputs, like, but that is probably less applicable, so that's probably why they didn't do so. But square root x is only defined for positive outputs, being that the square root of 16 can technically be 4 or negative 4, but they just define it as 4. So again, remember that the original input was negative 2, f of x, or f of the original input, is 4, and the inverse function gave us 2. These are not the same, and therefore these are not inverse functions. So when does a function have an inverse? And the function has an inverse if it passes the horizontal line test. And I'll explain the logic behind it in a bit, but let's take the line y equals x squared. If we put a horizontal thing in, there's two y values that can appear, and that is incorrect, because remember that once we take the inverse of it, it should give us the original input that gave us that y value. So if these y values are the same, let's just say that that's f of 2, and let's just say that that's f of 2. Well, I guess f of 2 is the same as f of negative 2, so I'm not going to denote that this is f negative 2. In other words, these outputs are the same, so when you apply the inverse function to it, it won't know which one to give you unless you define it, like the square root function. Like the square root function will only give you the positive x input. But since there's two inputs here, there isn't an inverse function, because it could be either one of these, and an inverse function isn't able to decide, as it's just a mathematical tool. So that's what you can't do. But if you define x squared as greater than or x is greater than 0, then theoretically, yes, that is. So like, this is y equals x squared. And then we'll do like a piecewise function for x squared if x is greater or equal to 0. And therefore, you can apply 1 because there is no two y values ever in the function. So yeah, let's move on. And these functions are called 1-to-1 if they pass the horizontal line test. So is y cubed 1-to-1? Yes, it is. It looks something like that. Actually, it looks probably something a little bit more steeper, or a little steeper, so something like that. But yeah, this function's 1-to-1 because it passes the horizontal test. So here's the formal definition. Well, I don't want to say formal because formal gets a little complicated with epsilon and delta proofs. But this is the definition that they actually give you rather than an explanation, is how I like to say it. Let f be a 1-to-1 function. So again, anything that passes the horizontal line test, f equals 1-to-1 with domain A. So I'll say D, A, R, B. Then the inverse function is going to have f negative 1 is going to have a domain of B where it takes all this input out and produces the original input back again. In other words, f of negative 1 of wait, f of negative 1 of f of x or y, so we could say the y, or f negative 1 of y will always give us x, and vice versa. Since f prime of f of x will always give us the original input back, or sorry, I guess I wrote it wrong. F of the negative input gives you just the input back, giving you just x, because this gives you, this is the inputs, or this is the output technically of the original function because the inverse takes the output, and this is the entire input, and then the function takes that input again and transforms it to give you the output. A little complicated, so let's do it for like an x cubed function. Oh, actually, no, we haven't got to how to find inverses yet. But in other words, f negative 1 of x will give you the original output that produced. So I guess, how do I explain this? F prime of, or sorry, not f, the inverse of f of x will give you the, I guess, the y value that makes x possible. The y value that made x value that made f of y come out with x, and then again it would just be f of y. So yeah, fy, so it's just going to be equal to f prime of x. Yep. Or f prime of y, where x is equal to f of y, pretty much. So that logic is pretty sound. It's a little bit difficult to explain, but I guess this one is a really important one, where the inverse of f of x, or the inverse of f of y is always going to be equal to x, and therefore f of x is always going to be equal to y. Pretty logical here. It's just swap notation. So let's start with a practical application or question. F of 1 is equal to 5, f3 equal to 7, and f8 is equal to negative 10. If assuming this is a one-on-one function, or one-on-one function, what are the inverse for each one? Or what is inverse of f? Inverse of 5, inverse of 7, and inverse of negative 10. Again, these are just going to give you the original input. It's going to be 1, 3, 8. Pretty easy, simple. So yeah. So how do you prove something is an inverse? Now to prove something is an inverse is quite simple. In other words, f negative 1 of f of x should always just give you x, because this is the inputs, produces the outputs. So input, output, and this one takes the output and transforms it back into the input. undoing what this original function did. Likewise, as mentioned before, f of negative 1 has the same logic here. This will provide the inputs, outputs, and again the inputs. So in other words, if x is whatever x is, f negative 1 of x, or the inverse of f of x, hold on one second. The inverse of the inverse of x will give you the y value in which x is possible. And then f of the inverse of x basically just cancels everything out, giving you back x as well for every x in B. So these are just domain restrictions. So yeah, again, it's just the same definition as before for every x in A and every x in B, because remember we defined the original domain of the original function to be A, the range to be B, and therefore the domain of the inverse function to be B and the range to be A. So f negative 1x, this is a little bit more difficult because we're assuming that x has already been evaluated by the function, but this basically tells you what input produces this output. So this entire thing tells you what input produces this output, and therefore this input will reproduce this output, and that is the logic behind it. So how do you find it? Or actually, let's do the proof first. Let's say f of x is equal to x cubed, and we're not going to learn about this right now. We're going to learn about this in a few minutes, but we know that the inverse is x and 1/3 using some simple, just algebra. We'll get to it later. So remember, f of negative 1 of x must equal x, and likewise f negative 1 of f of x must equal x. So f of negative 1x is simply just going to be cubed, and then put the f of negative 1x inside, so x to the 1/3, which is just x. Likewise, x third 1/3 is equal to x. So it is true, and you can prove it. But we'll move on to a little bit here. So we'll talk about how to find inverses, and this is quite easy as well. All it requires is all it requires is swapping x and y pretty much, but there's different ways that books do it. So let's say y is equal to, and they typically use y, which is interesting because they'll switch between y and f of x randomly. Like for implicit differentiation, they use y, but everyone tells you that f of x is the superior notation. So there's a few ways you can do it. So the book, what the book does is they first just swap y and x. So they don't first swap y and x. They solve for x first in terms of y. So it'll be x equal to y minus 2, just subtracting 2 from both sides, and then cube rooting it. And then they just swap the y and x, which is the same exact thing as putting y in first and solving for x, which is just going to be, or solving for y. Like what, x minus 2, 1/3. Again, it's the same thing because swapping it doesn't matter what time you do, pretty much, logically. The inverse function mirrors the original function over y equals x. That's pretty, so let's assume that the original function is this. Hopefully there's no overlap, actually, because there might be we'll assume that that's a 1-on-1 function, and we'll say that that's y equals x. Then this one's going to be like that. The logic being is that that every output here becomes the input here, and then the inputs become here. So it's kind of difficult to explain, but I believe how do I explain this? Remember the range becomes this domain, and the domain here becomes this range. So this domain here is going to be the range here. The range here becomes the domain, which is why it's mirrored over the x, pretty much, logically. So now what we're going to do is sketch f of x equals, this one's a little bit difficult as well because it requires radicals, or not radicals, but an idea of translation. So it's negative 1 minus x. This is pretty easy. I'm just going to simplify it to negative 1 of x plus 1. So as we know, if it's a square root function looks like this. But note that first we translated 1 to the left. So it's going to be negative 1 here. And then note that it's a negative 1, which flips the input here, which means that a number greater than negative 1, so like let's say 0.5, or negative 0.5. If we were plugging into here, this would be positive and therefore be negative, because square root of negative 1 of 1.5 is going to equal square root of negative 2.5, which is theoretically impossible. So any number greater than 1 will produce an error, because this will be positive, and a positive times a negative is always negative. So therefore we know it must be flipped this way. Again, always flipped over y equals x, so the other function is going to be this one, where you can use some logic here. Look, the domain becomes the range here, because the x value here becomes a y value here, because this one does whatever it does here. So like let's say that f of negative 1 here is equal to 0, it appears to be, and this is f of 0 is equal to negative 1, just simply reversing whatever it did. Pretty easy, pretty simple stuff. Now this is the calculus of inverse functions, and it's pretty difficult, or not pretty difficult, but I'm gonna go for the proof. So if f is a one-to-one function and is continuous, defined on an interval, then its inverse function f negative 1 is also continuous. Not to share the proof on that, but I'm just going to assume that it has something to do with one-to-one. But this is the proof that's quite difficult and quite tedious. Well, not quite tedious, but you don't have to know this, but I always find it easier to use equations when I know how they were derived. So if f is one-to-one and differentiable with inverse function f of negative 1 and f of inverse function f and inverse function okay, let me just write it out. If f is 1-to-1 and differentiable, which I'll just write here a table, with f of negative 1 and f prime of f of negative 1 is not equal to 0. And the reason why this is not equal to 0 is quite genius, actually. So if the derivative of f of negative 1 of a is equal to 0, then that means there's two y values. In other words, there's going to be two outputs produced here that will be the same thing, and that can't be possible because the domain and range are just swapped. So in other words, like let's take a function, let's do like x squared again, with x only defined on x is greater than 0, and that where this is the line y equals x, which is always a mirror image. And actually, let's not say it's x squared, because x squared does not fill these requirements. If there are two y values that are the same here, for an x value, pretty much. Because f of negative 1, the inverse function of a is, if the f derivative of that is 0, then that means f prime of a minus f of x over h is going to be equal to 0, which theoretically means that there are 2 points that have the same y value, such that the differential of dy over dx is equal to 0, means that dy is equal to 0. And remember, again, delta y can't be equal to 0, because the differential, because an inverse function has to be 1-to-1. If dy is equal to 0, then that means the initial and final position are the same. And again, that can't be the case with the inverse functions because they're 1-to-1. So that logic does not hold there, because f prime of 1 of a will give you the x inputs back of a. It takes in f of a and gives you f of x. Or it takes in f of a, or it takes in a and gives you back whatever made A possible. So that is science there behind that. So this is what is going to be quite difficult to understand and wrap your head around. So f negative 1 of A, or the inverse, I keep saying negative 1, is equal to, but this is also the derivative. So the derivative of the inverse function of A is equal to 1 over the derivative of the function with its input being the inverse function, like that. So let's start with the inverse relationship. So let's start with y equals f negative 1 of x, which we can swap in A for x later, so it doesn't matter. That means that f of y is equal to x, such that when you retake the input, you get the output. Right, because this is the output, which was technically the original input. So that means f of y, if it's equal to x, then this one takes the x and reverses it back to the original input. So that's the logic there behind that. We're going to differentiate both sides with respect to x. So all that means is going to be df of y over d of x, which is the derivative operator, is equal to 1, because we're doing it with respect to x. We have to use the chain rule because we don't know what f of y is technically. So it's just going to be d of x of f of y, and then times dy dx, which is the original, or yeah, which is just the input function. So inner outer, again, just chain rule. So we get that that is equal to 1. And all we do is dy over dx is equal to 1 over, because we're just going to divide this on both sides, equal to 1 over dx of f of y. And then y is equal to f negative 1 of x. So that basically means that f negative 1 prime of x, f negative 1 prime of x is equal to 1 over f of f negative 1 prime of x. So just to prove using derivatives in chain rule. So that one's pretty easy. So let's do a practice question. If f of x is equal to 2x plus cosine x, find f negative 1 of 1. Yes. Okay, so first let's start off using some logic here. There is no inverse function for 2x plus cosine x. Because first it isn't 1 to 1, obviously. But also using some logic, like seriously, how would you isolate x here? You can't factor an x out because x is an input here, and x is just out here like that. So you can't do anything with this. But we can use some logic because we know that f negative 1 of 1 so all we're going to do is take the point 1 here, because this is technically the output. So because we're going to take the output and reverse the input, it's going to be 1 2x plus cosine x. You could solve this graphically, or you can use some simple trigonometric logic to assume that 0 will just cancel this term out and cosine of 0 is just equal to 1. So that means x is equal to 1, such that the point here is 1 comma 0, such that f of negative 1 of 1 is equal to 0, because it takes, or sorry, not the derivative, such that the inverse function of 1 is equal to 0 because it just takes the output and reverses back to the input. So that means we have the point 0, I guess it would be 0 comma 1, because again it's the output. So yeah, let me just reverse that real quick. So it's gonna be 0 comma 1, because 1 is the output. So again, we can just apply the rule that well, first let's find what f prime is, because that's important for the definition. And f prime is going to be equal to, just use basic calculus here. Actually, cosine x is negative sine x, so it's going to be 2 minus sine x, which is derivative. Pretty simple stuff. So let's do f negative 1 of 1, f prime negative 1 of 1, which is going to be just 2 minus sine 1, which is just going to be, or not 2 minus sine 1, it's going to be equal to 1 over f prime, which is just going to be 2 minus sine, and then the inputs, which is just going to be 0. So that means that f negative 1, the inverse function, the derivative of the inverse function at 1 is going to be equal to 1/2. So that's pretty simple there. Just difficult to wrap your head around the proof, but it's whatever. That one's just quite simple. Let's take a logarithmic function, and we'll take y is equal to x. So just equal to that again. So remember that f of x is equal to a of x, which is the exponential notation. But that means that the log a of f of x is equal to x. So again, they define the log as kind of an inverse function of the exponential function. So that's the logic there. In other words, ay is equal to x, and y is equal to log a of x, which is pretty self-explanatory, because you can rewrite x as a form of a to the power of whatever, and then just log both sides. So ay equals x probably looks something like that, as we've gone through exponentials. And the last one, the logarithmic function looks like that. So it's, again, just, actually, logarithmic function will look something like that, which means that this will look something like that. Right. Perfect. So the domain of log a, or sorry, not the domain. We're just going to go over formal definition, not definitions per se, but rules. Log a of ax is just going to be equal to x because this logarithmic function basically checks how many to what power the input is of the base. So it's going to give you back x, but only when x is all real numbers. And remember that x can be any number it wants theoretically, because even negative numbers work as well. Now, a log a of x is the same thing, but we apply the definition here where we swap the domains. So for, and remember that logarithms only work for sorry, it should be a to the x. Logarithms only work for positive numbers, so it's going to be for every x greater than 0. Just because wait, actually, hold on one second. I don't think this is true, actually. 1 second. Actually, yeah, so it's for all real numbers as well. I'm not too sure why my textbook said that, but I don't think it was textbook. But yeah, you just swap domain and range. And as we know, the domain of a to the power of x is going to be 0 to infinity. Yeah, 0 to infinity assuming a is positive. And x, so this is for positive ones. And x, and the range will just be 0 to infinity, while the input is negative infinity to positive infinity. And since these are just inverse functions, or just canceling it out, x is all real numbers pretty much. And I can use some logic there to denote the domain and range. Lastly, we have the laws of logarithms, which is quite easy. log a xy is equal to log a x plus y. I can do proofs on these two, but it's pretty easy. Log a of x over y is equal to log a x minus log a y. Log a of x to the y power, or r. The book says r, but I'll just use y for consistency, is equal to y log ax. So let's go over why this is the case for that one. So y is just simply going to be, in the first one, a base of x that we don't know, pretty much, logically. So let's just say it's going to be equal to x to the z. Then you just add the things such that this is the same thing as a log a of x, 1 plus z. And if you take the log a, this is going to be equal to log or actually, I guess the better definition or way to prove it would be that x would be equal to a to a certain power. So let's just say ax plus a y, or ax times ay, which you can just write as log a x, or log a x plus y, which is just going to be equal to x plus y. But obviously I took a shortcut there, so yeah, that's the logic there. X divided by y, you just subtract the exponents, which is y. It's the same thing here. Log ax to the power of y multiplies the exponent, meaning that it will multiply the input as well, which technically becomes the output here. That's the logic there. These are the laws, logarithms, pretty simple stuff. Change of base, this is really not necessary anymore, but I guess they use it. I'm not too sure why. Well, we have to remember that calculus was done in the 1700s and such, and 1800s and so on and so forth, such that they don't have they didn't have calculators back then, which is why linearization is really interesting. But anyways, log a of x is gonna be equal to log x over log a with b right here, such that b can be any real number greater than 0, because you can't take a negative logarithm. Well, actually, technically you can, logically, but basically you can say that like log 4, or I guess log base 10 of 20 is going to be equal to log 2 of 20 over log 2 of 10. The proof there is, I did this last year, but I don't remember necessarily, so that is the logic there behind that. So those are just calculus 2.2, or 3.2 actually.